Now you know Scheme. And so we're going to do an extended example that has something to do with what I actually work on in my life, which is natural language processing. That's computer applications that have to do with working with text that represents human languages, like English or Chinese. So one thing that we do in natural language processing is that we try to figure out the structure of a sentence. And a structure of a sentence can be described by a tree. And each subtree is called a constituent. So we're not going to use sentences today, we'll just use some phrases, but a long noun phrase is an English phrase with the following structure. So there's a constituent within it that says noun phrase, and then there's a long noun phrase. So it's not a long noun, but a long phrase, and it's a long noun phrase. So these are all structural components. Each tree describes a constituent, and the whole thing is a noun phrase. A noun can have a two-word modifier, and in this case we have a different structure. So it's not a two modifier, but it's a two-word modifier. Some trees are balanced, and they look like that. The other trees lean, so this would be another tree that leans a little bit. And there are just so many trees that exist. So many modifies trees. So many trees exist. So here are 5 different structures over phrases of 4 words in length. So here's a question for you. How many trees are there over K leaves? If we assume that the tree is binary, meaning every tree either has 2 branches or it's a leaf itself. Well, here's one way to go about counting up all of these different trees. We can pick how many leaves are going to be in the left branch versus how many leaves are going to be in the right branch, because they all have to be at one place or another. So if we ask, what are all the trees where we have 1 in the left and 3 in the right? Well, it turns out that they correspond to these 2 structures here, and we can enumerate the different ways of having 1 tree in the left. Well, that's just a base case. I mean, when you only have 1 leaf, then there's only 1 tree that could possibly describe it. But the other branch, the right branch, is going to have 3 leaves, and there are 2 different ways of doing that. We could have that structure, or we could have that structure. In addition, we could split the 4 leaves into 2 and 2. And there's only 1 tree that works in that structure. Or we could split into 3 and 1, and then we get these 2 trees over here, which are mirror images in a way of the trees over there. So that gives a general recursive pattern for how I could count up the number of different trees that have K leaves, or 4 leaves in this case. So here's what we'd like to do next. We'd like to come up with a recursive statement that says the number of trees over n leaves in total, 4 in this case, with K leaves in the left branch and n minus K leaves in the right branch is what? The answer should be an expression that refers to the number of trees over K leaves and n minus K leaves. Here's the solution. We multiply together the number of different ways that we can draw a tree over the K leaves on the left by the number of ways that we can draw a tree over the n minus K leaves on the right, because we can combine any one of the left trees with any one of the right trees to form a full tree. And so we can write a function that does just this, counts the number of ways of drawing a binary tree over a sequence of n leaves. Okay, so this time we're going to write our solution in a file and then load it into Scheme. So if I write square x in a file called x.scheme, and then I load x.scheme, then it will say okay, and I can square things. Excellent. But instead of squaring things, what we'd like to do is count trees with n leaves. Count the binary trees with n leaves. We've learned something already. Semicolons introduce comments in Scheme. Okay, so we're going to need to be able to count trees that have n leaves but exactly k in the left. Count trees with k in the left branch. And the expression that we wrote down for how to do this is we multiply the result of counting trees that have k leaves with the trees that have n minus k leaves. Okay, so how do we actually express iteration? We want to try all the k, starting at 1, and going up until n. Now there's no range and there's no for statement in what we've talked about so far, but we can define a recursive function that sums things together. So let's write down count after k, which is count trees with at least k in the left branch. And here we'll have a recursive definition where the base case is when k is all the way up to n. Then we don't have any such trees. Otherwise, we want to sum together what happens when we count the trees with k in the left branch, and we count all the ones that have at least k plus 1 in the left branch. Okay, so what do we have so far? We have a recursion of count with that calls count trees. Count after is really just a way of summing up all of the different calls to count with. And then we want one more base case, which is what happens if we count all the trees with just one leaf. So if n is 1, then there's only one tree that has one leaf. Otherwise, we can start with k is 1 in the left and some number in the right, and count all the trees with at least 1 in the left. So that would be count after 1. Let's load this file and see what it does. So if we count trees with 4 leaves, we should have found the 5 that we saw before. And if we count trees with 5 leaves, we find that there are 14, because we can have arbitrary combinations. 1 on the left, 4 on the right, well then we have 5 different of those. If we have 4 on the left and 1 on the right, we have 5 more of those, so that's 10 in total. And the other 4 have to do with whether or not you have 2 on the left and 3 on the right, or 3 on the left and 2 on the right. And this number grows quite quickly. So if you look at all the trees with 7 leaves, that's a fairly large number. 10 leaves starts to take a little bit to compute. Now, why is it taking so long to compute something so simple? 2 reasons. This is tree recursion, and therefore has exponential growth. The other reason is that I'm running this example using an interpreter that's running in Python. It's in fact just the interpreter that you will build when you finish your project 4. The scheme project is to define the program that actually executes all of this code. So we will have to know how to define things and how to evaluate call expressions and if expressions and everything. And then all of a sudden, you can write programs in a programming language that you define in your own interpreter to do things like count trees.